Hello, my friends. Welcome to today. Unfortunately, I cannot be there with you. I'm bummed out about it. I'm sure you're totally bummed as well. But we do need to move forward. So I put together this little video for us so we can do that. Do me a favor and take out your lab notebooks. Open up to the lab we were working on. It's Getting Pushy Lab. The Getting Pushy Lab, we will be picking up there and moving forward. So underneath your data table, there should be some space in your lab notebook. We're going to draw a quick force diagram of what's going on when we're out in the hallways pulling. Now, I know some of your groups I've been able to get around to on Tuesday to help clarify some of the data. It is notoriously tricky to measure well with those spring scales, and it's kind of hard to tell if you're going the same speed. So today we're going to talk about some of the conclusions we should reach with this lab. And maybe even some of the things we didn't reach and why. So first of all, I've drawn the floor, and I'm going to draw a force diagram of a person being pulled on a cart. So I'm going to first draw a cart, and I want you to draw this as well right below your data table in your lab. I'm going to draw this force diagram. Bam. Now at this point, I actually have a cart. I don't really need to put a person on it. So if you're like, I don't want to draw a person, I'm not very good at it, you don't. The same forces apply whether there's a person or not. It'll just change the size of the forces. But I'm going to go ahead and draw my person. So if you want to, so that's the foot if you're wondering. You're like, what is that thing? And I'm going to go like this, and I'm going to go like this, and I'm going to go like this, and this. And then I'm going to put an arm here. I'm feeling pretty good about this. The head's where things go sideways. And yep. That's where things went sideways. I'm going to give them some hair. And then the hands go sideways. Yep, look at that. That didn't go well either. But I was pretty stoked. It's kind of out of proportion here a little bit. Whatever. Don't judge me. So maybe like, ooh, look at that. Look better. How else could I make it? Ooh, I could put a belt on them. No. All right. So I guess what I'm illustrating here is what not to do in a force diagram. Don't spend too much time making your object perfect. We want to spend more time on forces. And the more stuff you draw here, the harder it is to put the arrows in later, so it's actually a bad thing. All right, so now we have this thing drawn. Let's figure out, and this is forward for us, right? So here's forward. Let's figure out what forces are acting on the object. So first of all, here's the floor down here and the cart and everything else. We're on Earth, so the one easy one we should always get is the force of the Earth pulling down. Force of the Earth. Okay. Now the next other thing about is this thing falling? And if this thing isn't falling, which it isn't hopefully, there must be a force that's acting against the Earth here, and that's the force of the floor pushing up. So that's the force of the floor pushing up. And this is when you fall down and hit the ground, this is the force you feel pushing on you, and this is the force that hurts you. It's not this downward force of the earth that you feel, it's this upward force of the floor pushing on you. And I can maybe prove that to you. If you were to climb up to the top of a building and jump off, you would suddenly feel weightless. You'd be like, oh, so cool. All you would feel was wind pushing against your skin. Even though the force of the earth is still pulling you down, you don't actually feel this force as much as you feel the floor pushing up, and you will feel that when you hit the ground at some point. So those are two obvious forces we got to get right away. Make sure we have those squared away. And the next one is there's a force of a person pulling. So instead of drawing a whole spring scale here, I'm just going to draw a force of the spring scale, and then label that with the spring scale. Because that's the object. Even though there's a person pulling the spring scale, the force on this person is the spring scale, not the person. It's being transmitted through the spring scale. Now the question is, hey, what are you pulling against? Right? So we've got this spring scale, and we pull, and it's like hard to pull the person. But it's not too terribly hard. It's like reasonably hard. And then ask ourselves, well, what if we didn't have a cart? Would this be easier or harder to pull them? And of course the answer is harder. And we get to at some point the realization that what we're pulling against here, why we have to pull on them, is because there's friction. Even in these carts there's some friction. Now that frictional force is going to point against us. So I'm going to put it down here by the wheels and say, okay, there's a force down here pushing backwards against us, resisting our motion. And we got to figure out what we're going to call this force. What object causes this force? Let you think about that for a second. What object causes this frictional force backwards? Maybe you concluded, hey, there's some bearings in here, and there is, as the wheel rolls around, the bearings rub and cause friction. And I would say, okay, that sounds terrific, so we would write force of the bearings, but then I think, wait a second, what if I made the force super slippery so that the wheels don't even have to turn, they just slip across? Would there be any friction? And the answer is no. So, but the bearings would still be in there. So it's not really the bearings that are causing the friction, it's really the wheels grinding on the ground, making those bearings turn, which causes the friction. So I'm going to say here, this is the force of the floor, right? And this is floor, and in parentheses, I'm going to put here friction, just to remind me what that is. So it's the floor, really the floor is doing the force, but it's friction. So this is the realization that I come to here. Boom. That's my force diagram. There are four major forces acting on the cart. There's the friction opposing motion. There's you pulling forward. There's the floor pushing up. There's the earth pulling down on you. And those are those four major forces. Now, one thing that we may not have gotten, and this is actually tricky to get. In our data table, we were supposed to be collecting data on slow force, so how much force it takes to go slow, measuring that newtons, and fast pull force or medium pull force, I think I told you. Because fast, you tend to fall down and have the cart crush you and roll over you. So let's say our slow pull force was 20 for this person. This is, I don't know, this is, Bobby. And this is Jane. Awesome. I should probably use a name from the class. Oh, well. And let's say Bobby was 20 newtons and Jane only took 15 newtons. Now, I think the normal thing to think is that if slow took 20 newtons for Bobby, it should take something like 25 newtons for fast. And for Jane, if it took 15 newtons here, it should take, I don't know, 20-ish newtons. It should take a little bit more, maybe 18 newtons for Jane. I think that's a reasonable thing for people to think. And what we're going to find in this lab, and if you haven't already, I know I've got some of your groups already, it's so easy to mismeasure in this lab that you make yourself convinced that it really is more. But when we do a careful job of this lab, and I want you to do this Friday when we have a chance, what you find is it's not 25, it's not 20, it's not 18. What you find is to keep a constant speed, whether you're slow or fast, requires the same force. So at 15 slow, it would be 15 fast. If it was 20 slow, 20 fast. Now, if you didn't get those results in the lab on Tuesday, what I want you to do on Friday, first thing, is you're going to go out and roll those carts again, get a really good slow pull force, and then just verify that the same force, if you speed up, pulling at the same force will keep you at that new higher speed. It's a really kind of cool result. And the reason for that is to stay at a constant speed, you need to have your forward force of the spring scale equal the backwards force of friction. Because when that happens, it's as if these two forces cancel each other out. And we know that if objects aren't experiencing any forces, when there's no outside forces, objects in motion, in motion, stay in motion. So by pulling forward as hard as friction pulls backwards, you're basically canceling out the friction with your forward force. It's as if there are no forces and objects in motion just stay in motion. If they're slow, they stay in motion slow. If they're fast, they stay in motion fast. The key is to pull the same on both of them. And you know you're pulling the same when you're going at a constant speed. Because at a constant speed, they must be the same, otherwise it would do something else. So that's kind of a cool thing to do. Yeah. So check your data table. If you've got different forces for slow and fast, you're going to need to be able to just pull one more time for this lab on Friday, right at the very beginning. If you have the same forces on both, you're squared away already. But if you don't have the same forces, I do want you to have the experience of actually pulling and getting the feel that they really are the same force. Okay. I think that does it for the lab stuff. So at this point, what I want you to do is I want you to work on your post-lab questions, and our guest teacher today will pass those post-lab questions out to you now, and then I want you to work on them. But when you work on them, I want you to work as a collaborative, like POGL group. So elect someone in your group to be the manager, and then manager, you're going to read each question aloud, give time and space for people to be able to discuss it and come up with an answer and work through those. My guess is those take us maybe 10 or 15 minutes to accomplish. So until then, let's pause the video. When that gets all done and we're ready to move on, go ahead and hit play again. Awesome, welcome back. So we've done all of our post-lab questions. I wanted to just really briefly go over a couple of them with you. So if you can pull that out, make sure your post-lab questions are open and in front of you. Basically, the big idea here is trying to establish this this need to pull the cart is based on the fact that there is friction with the cart, and that backwards force of friction is the force that's fighting you, and you have to pull with, to keep the cart going at a constant speed, you've got to pull with a force equal to friction. So be checking on that stuff. And when you do that, it's as if you've canceled out the friction, and it's like you're on a friction-free surface, which means if you're in motion, you just stay in motion. It's a beautiful idea. Number 3 was the force diagram that we actually drew in the slides just a second ago. Hopefully you saw that was the same thing. So make sure that's drawn in there as well. If the wheels were old and rusty, of course it would be more friction and there would be more pull on the floor, and it would be harder to keep it going. It would require more forward force to make up for the more friction that's backwards. You got to always match the friction to stay at constant speed. If we had put a huge fan at the end of the hallway and turned it on, just blowing a bunch of air down, you would also need more force, because now you would have friction to pull against and you would have air resistance to pull against. That'd be 2 forces, and you have to balance both those backwards forces to keep the cart moving at a constant speed, because you need to make sure there's canceled out forces on it so that there aren't any unbalanced forces. And then 5 was probably a surprising result, and for some of you maybe you haven't gotten that result yet, and that's that, hey, as long as you're balancing out friction, you go constant. Whether that's a constant slow or constant fast just depends on how fast you're going when you balance them. The moment you balance out the forces, you pull the same as friction, that cart stops doing anything but just going constant. It's just like, boom, constant speed at wherever you were, right? So if you did that when you were going slow, you keep going slow. If you did that when you were going fast, you just keep going fast. Doesn't matter. Does it not matter? All right. So next what I want you to do is I want you to work on a few pages in your homework packet. I think you've done some of this work already, but pages 8 and 9 in your homework packet are force diagrams. Like I said, I think some of you have already done this work. If you have, yay for you. We'll check that probably next Monday. We'll check that. And then also pages 10 and 11, I want you to do those as well, and those are called Newton's first law question. So those are 2 things I want you to work on right now. When we feel like we're getting those things squared away, actually, you know what, before we do that, let's do one other thing. Let's tape in the next lab in our lab notebook. So right now what I want you to do is tape in it's a lab called the Cart Mayhem. Whoops. Oh, did not spell that well. Cart Mayhem lab. Tape that thing in. It's 2 pages. They look like this. And actually, most of you have this already. So check your lab notebooks first. I gave it to you accidentally before. It looks like this. And the second page looks like this. So try and find those in your lab notebook and get those out. Tape those in on the next open page. Do that now. And you're going to work with your lab group. So tape in Cart Mayhem. And then you're going to work on the read the introduction, read intro, purpose. Don't forget to read the purpose. It's important to understand why we're learning what we're learning. And then also do the pre-lab activities. So pre-lab activities. And that's number 1 through 5. Now once you're done with all of this down here, then you work on pages 8 through 11 in your homework packet. These are due on Friday, and we'll stamp them as soon as we can. All right, so have a great day today. Work hard, do the right thing, and I will see you Monday. Have a great weekend. I will also see you Friday if you're wondering. All right, bye-bye.